This website makes learning so easy. I found all my resources here.
Welcome to The Explainer. Today, we're diving into something that is honestly one of the most notoriously complex, mind-bending subjects in all of science. Yep, we're talking about quantum mechanics. But don't worry, we're going to break it down step by step to see exactly how the universe operates at the absolute smallest possible scales.
To really set the stage here, I want you to think about a warning from the legendary quantum physicist Richard Feynman. He said, "Nature as she is, absurd." And he hit the nail on the head. Our everyday intuitive logic, the way we just expect baseballs to fly through the air or water to flow out of a tap, that completely breaks down at the microscopic level. What we're about to explore literally defies common sense.
So here's our roadmap for this descent into the absurd. We'll start with when classical physics failed, then move on to discovering the quantum realm, outline the weird rules of reality, explore fields, forces, and entanglement, and finally, look at quantum tech in everyday life. Let's get into it. Section 1. When classical physics failed. You see, right toward the end of the 19th century, scientists started realizing their trusty old rulebook was actually missing some pretty vital pages.
There's just this incredibly stark contrast in how our universe behaves depending on how close you look. On the macro scale, classical physics dictates all those intuitive behaviors we're used to. It handles things we can actually see and touch, all the way up to massive astronomical bodies like the moon. And hey, it is wonderfully reliable for our everyday human experience. But zoom into the micro scale and quantum mechanics takes the wheel. We're talking atomic and subatomic particles here. At this scale, scientists quickly discovered that behaviors become completely counterintuitive. Classical physics just flat out couldn't explain what was happening.
Moving to Part 2, Discovering the Quantum Realm. We're going to follow the breadcrumbs left by some truly brilliant physicists to see exactly how this microscopic world was uncovered.
This wasn't an overnight thing. The transition was really a gradual buildup of groundbreaking ideas. Back in 1900, Max Planck was studying blackbody radiation and theorized that energy was actually spread among these discrete oscillators. Then, around 1905, Albert Einstein takes us a step further, proposing that light itself was corpuscular, basically made of individual energy quanta. Fast forward a bit to 1913, and Niels Bohr discovers that electrons inside atoms have constrained orbits. That means they can only absorb or emit very specific amounts of energy. And then in 1927, Werner Heisenberg really cements the weirdness by proving his famous uncertainty principle. So what's the grand takeaway from all this? Well, over and over again, energy and matter were found to exist in distinct, discrete chunks, or quanta, rather than as continuous waves.
Which brings us to Section 3, the weird rules of reality. Now we're going to shift gears a bit and dive right into the core paradoxes of nature that actually dictate how this microscopic space operates.
Let's start with wave-particle duality. This is the wild concept that neither the classical idea of a particle nor a wave can fully describe the behavior of quantum-scale objects. Things like light and matter, they actually possess both wave and particle characteristics. And here's the kicker: which one actually manifests depends entirely on how they are measured.
The famous double-slit experiment really reveals just how bizarre this gets. When a system is unmeasured, it acts just like a wave, passing through two slits and producing this classic interference pattern of light and dark bands. But the mere act of measuring it completely alters reality. When it's measured or observed, it acts like a particle. It shows up as a specific individual dot on a detector screen. Let that sink in for a second. The universe literally changes its behavior just because we're watching it.
That mind-bender brings us right to another foundational rule: Heisenberg's uncertainty principle. This is the rule stating that certain pairs of physical properties, like position and speed, cannot be simultaneously measured to arbitrary precision. And the absolutely crucial point here is that this isn't just some flaw in our measuring equipment. No, this is a fundamental trade-off inherent in nature itself. The more precisely you measure one property, the less precisely you can possibly know the other.
To really grasp this kind of abstract mathematical concept, just think about an everyday radar speed trap. If a cop clocks a car in a speed trap, they know its exact position and its speed simultaneously, right? But for an electron, it is a completely different ballgame. To find an electron's position, you might try to bounce a photon of light off of it. But that collision transfers energy, which drastically alters the electron's momentum. So the very act of finding its exact position inherently destroys your knowledge of its speed.
So what actually happens when we finally do make that measurement? Well, we trigger what's called a wave function collapse. This is the phenomenon where making a measurement literally forces a probabilistic quantum state into a definite measured value. See, before a particle hits a camera sensor, it's basically just a fuzzy set of probabilities. But the very moment it interacts with the detection device, its wave function disappears and it definitively snaps into reality as a concrete, macroscopic physical change.
Okay, moving to Section 4, Fields, Forces, and Entanglement. Let's scale up the weirdness a bit and explore how these microscopic rules actually expand outward to govern the fundamental forces of the entire universe.
Consider quantum entanglement. It's a state where particles interact in such a way that their quantum states just cannot be described independently from one another, even when they're separated by incredibly large distances. Now, Einstein notoriously hated this idea. He famously called it spooky action at a distance. He firmly believed that measuring one particle couldn't possibly instantly correlate with its partner without violating the cosmic speed limit, the speed of light.
But as it turns out, Einstein was actually wrong on this one. The physicist John Stuart Bell deduced a specific mathematical inequality, and later experiments proved that nature absolutely violates it. Basically, this means nature disobeys what we call local hidden variables. The results definitively confirmed that reality at this microscopic level truly is non-local. Entangled particles genuinely do interact instantaneously, no matter how widely they're separated across the universe. Crazy, right?
So, to bring all these interacting particles and fields together into one cohesive picture, physicists use a framework known as the Standard Model. And it is a massive, massive success. It beautifully explains electromagnetism, weak interactions, and strong interactions. However, it still completely misses gravity and dark matter. So while it's an absolutely monumental achievement for science, it still falls a bit short of being that elusive theory of everything.
Finally, Section 5, Quantum Tech in Everyday Life. Let's bring you back down to reality for a minute. Let's answer, why does this actually matter? And look at how this totally absurd physics is quietly powering your daily life.
Ever wonder why you can get a really nasty sunburn at the beach, but if you sit under an infrared heat lamp, you just get comfortably warm? Well, it is purely due to quantized photon energy. You see, ultraviolet photons are high-energy quanta. They deliver enough packed energy to cause actual cellular damage. But infrared photons, they're low-energy quanta. They only carry enough energy to provide a little bit of surface warmth.
In the real world, applications go way beyond just avoiding sunburns. Everyday quantum tech completely surrounds us. I'm talking about lasers, the microscopic transistors running the very device you're using to watch this right now, and MRI machines in hospitals. Literally, none of these technological marvels would exist without our deep understanding of macroscopic quantum phenomena.
Now this next one is a total aha moment. The flash memory in your USB drive, and honestly even simple light switches, rely on something called quantum tunneling to pass electrons straight through physical barriers. I'm serious. If electrons didn't occasionally act as probability waves that can just tunnel right through an impenetrable oxide wall, we wouldn't be able to erase data on memory cells. Simple switches wouldn't even work. We are literally harnessing microscopic teleportation just to save our files.
And that brings us to the end of our explainer. Here's the thing. The math of quantum mechanics works absolutely perfectly, but the interpretations of what it actually means are wildly different. So I want to leave you with a thought to chew on. Are we living in a multiverse, the many worlds interpretation, where every single quantum probability branches off and creates an entirely new universe? Or is reality simply meaningless until the exact moment we measure it, like the Copenhagen interpretation states? It's enough to leave your mind completely reeling, right? I really hope this explainer has sparked your curiosity and left you eager to learn even more about the beautiful absurdity of our universe.
This website makes learning so easy. I found all my resources here.